Various reactions of propane are given to us in this schematic that we see. Many familiar reagents are given to us in this question, such as UV light and chlorine gas, aqueous sodium hydroxide, polymerization. All of these terms should be very familiar. We are first required to identify which of the reactions is a free radical substitution, which is electrophilic addition, and which one of them represents elimination. Now, before we try to actually answer any of the questions given to us over here, let's just have a look at which parts of the molecules have actually changed. So if we look at this part over here, we have a methyl group at the end of the molecule, but now we do not. Similarly, we have a chlorine group over here, but now we have an OH group over here. And again, looking at reaction free, the chlorine group here is now changed into a carbon-carbon double bond, and last of all, this carbon-carbon double bond has now changed into an alcohol group. So let's try to first of all understand what the term free radical substitution means. Free radical substitution means replacing one part of a molecule with a free radical, and in order for that to happen, you must first of all generate a free radical, and the conditions used to generate a free radical are given to us over here, which is chlorine, gas, and UV light. So instantly, whenever you see chlorine and UV light, you know you are undergoing a free radical substitution. Therefore, this must be reaction 1. And if you look carefully, the hydrogen over here is being replaced by a chlorine. We have 3 hydrogens here. Now we only have a chlorine and 2 hydrogens. Electrophilic addition represents the addition of a molecule across a double bond, and there's only one instance of having a double bond in this reaction sequence, which is given to us by molecule C. And if you look at C to D, you will see that you've actually added across one hydrogen at the end here to go from CH2 to CH3, as well as adding an OH group over here, as can be seen in D. So altogether you've added one hydrogen here, an OH from here. So what must have happened is that we've added H2O in this reaction here. And finally, elimination means the removal of a part of a molecule. And if you look at reaction 3, what we've done is removed one hydrogen from this carbon here. So we're going from CH2 to CH, and also we're removing the Cl from here to leave CH2. So from here we've lost a hydrogen chloride molecule. Definition of a nucleophile is straightforward from your textbooks of scheme of work. It's a lone pair donor or electron pair donor. The key part here is to ensure that you do not miss out the word pair. This is indeed the most common mistake students make. They leave out this virtually important word pair. This question talks about the mechanism of a reaction, a typical area where students find difficulty. What is essential here is that students must take into account the origin of the curly arrow as well as destination of the curly arrow. Same applies to the curly arrow, which is then departing to form the Cl minus over here. You also need to remember the direction of the curly arrow. It always originates from the center of negative charge and always goes towards the positive charge or the partial positive charge. Same situation here, originates from electron source or the covalent bond in this case, and going towards the electronegative element, which is chlorine. Definition of a structural isomer, again straightforward from your textbook or from your scheme of work. Same molecular formula but different structure. For drawing the skeletal formula as given in the mark scheme here, the best thing to do is actually look back at the structural formula and expand on this to generate the displayed formulae. So what we'll do here is we'll highlight the length of the longest chain first. Remembering that every corner and end represents a carbon, so this end is a carbon, this corner is a carbon, this corner is a carbon, and that's the end of the chain there. And if you look carefully, what you have in this highlighted line here is very similar to what you have in the skeletal formula. Remember, you have to put in the OH group at the end, as the only things you do not put in the skeletal formula are the main carbon hydrogens on the backbone. And if we do the same thing to the second molecule, like so, again we have something very similar to what we had in the previous case. So looking at this molecule over here, we have carbon in this corner, in the center, and at the end over here, exactly how we had it over here. Whenever asked about polymerization at AS, the answer will always be addition polymerization, being careful never to quote the word additional. Again, this is a very, very common mistake that students make, so just make sure that that is always avoided. When queried about the name of a polymer, this should be relatively simple. You always quote the name of the monomer, which in this case is propene, and then stick the word poly before the name of the monomer. So the polymer name is derived from the monomer. In the next question, you're asked about 2 repeat units of polypropene. Again, this is relatively straightforward. We have 1 repeat unit over here, and the easiest way to figure out what the monomer is to actually take this bond and collapse it back there. Take this bond, collapse it back, and that would give you the original monomer, which would have been propene. Another mechanism question, again just be careful that the arrow originates from the lone pair and the destination is the delta positive carbon, and another reminder, one arrow coming in means another arrow going out, as well as a Cl minus being formed at the end, which is a result of this process of bond breaking over here. Part B is a very straightforward empirical formula question. I'll just quickly run this through to tell you how it's worked out. You're given the amount of carbon, so carbon is 37.8 divided by 12, and that should equal to 3.15. And then you're given the amount of hydrogen in the question, which is 6.3 over here, so we can work that out. So hydrogen is 6.3 divided by the relative atomic mass of hydrogen, which is 1, and that will remain 6.3. And last of all, you are given the amount of chlorine, 55.9. So chlorine is 55.9 divided by 35.5, and that equals 1.58. The next step is to divide each of these numbers by the smallest of the 3, which is 1.58. So we're going to divide 3.15 by 1.58. We'll divide 6.3 by 1.58. And finally we'll divide 1.58 by 1.58. And that should leave us with the amount of carbon being equal to 2, because 3.15 divided by 1.58 is 2. And then we have 6.3 divided by 1.58, and that will give us a figure equivalent to 4. And lastly, 1.58 divided by 1.58 will equal to 1. The empirical formula therefore is C2H4Cl, just as we have quoted in the mark scheme over here. How do we get to the molecular formula? Well, we're told in the question that the molecular weight or mass is 127, and if you add up all these figures over here, you'll end up with a figure of 63.5, which is exactly half that of 127. So therefore the molecular formula must be double this figure here. So you multiply everything here by 2 to end up with C4H8Cl2. How to draw butane 1,3-diol? Well, let's first of all start off with the longest carbon chain, which is but, which is 4. So 1, 2, 3, 4. We have an OH in 1 and 3 position. So this is position 1, 2, 3, 4. And you can clearly see that we've got OH on position 1 to satisfy this. OH in position 3 to satisfy the 3. Di because there are 2 OHs, and ol obviously because of the OH. How do we figure out the structure of H? Well, we're told in the question H can be hydrolyzed with hot aqueous alkali to form butane 1,3-diol. If we're forming 1,3-diol, we must have had the chlorines in, again, exactly the same positions, which is 1 and 3.